So I will start with hair braids, because usually when you hear about the word braids, you think hair braids. You don't think about mathematics. And then I will also tell you how I got interested in braids and how did I find the connection between braids and art. And then we go to the great master of Leonardo da Vinci and other Renaissance artists, and mathematical braids, Leonardo dynamic drawing of braids, the sentence of the day. Every time I'll put one sentence, whenever I talk to you, sentence to remember. It could be about female in math, it could be about math, it could be about anything. And then, if there is time, I'll do two appendices. One about Leonardo and the golden section, if you are already talked about appending, a machine vision, another one. And then I'll give you preview to the weekend that will come in the spring, because there will be another weekend like this in the spring on a different topics, and those two together will be considered like instructor reading for, so you get one college credit for that. And I just forgot to mention before that I said that it's a great privilege what you get here, but you were selected among the top students in mathematics in the College of Art and Sciences. So, and we kept it, one for COVID reasons, and one in order to have an intimate conversation and to be able to arrange the mentorship. Okay. I lived a couple of semesters in Harlem in New York, so I learned a lot about braids, and I tried even to do braiding of my hair. But these are not photos that I took myself. These are photos that I found. This is 3 strands braid. This is the regular braid that we know. We take the hair, we divide it into 3 strands, and we start to do it. Probably almost all of you did it at one point. Yesterday evening, one of the students that participated said she was always fascinated about braids, but we all try to do all sorts of braids, and she didn't know it's a mathematical object. This is 4 strands braid, so you start with 2 of them and you put them together. And this is a mixed strand braids, because some of them are 2 strands, 3 strands, mixed strands braid. That also has a mathematical meaning. But this is just to ease our way into the braids. So how did I get interested in braids? As was mentioned, I was algebraic geometer. And I was interested in the structure of all sorts of surfaces and high-dimensional bodies. The shape. At some point I did even 10 degrees. We are like in a world of 3 dimension, so I took also 10 dimension and shape of the universe concerning to physics, etc. Very large thoughts about large things. And then I was in the Institute for Advanced Study in Princeton for my postdoc, together with one of the speakers that you will meet here, Professor Rick Miranda. And there, someone came and gave a talk about how to use braids, and it was very technical, and everybody said, no, it's technical. I said, what do you mean technical? Mathematics can be technical, but people like mathematics as ideas many times. You can go to a class of mathematics and don't see a number anyhow. So the Greeks started with geometry that doesn't have numbers, but we always have to somewhere do calculations. So I said, okay, let's go for it. And I said it's a lot of calculation, but there must be some geometry in the back. So I went into, and then I found out that it really was very helpful in the study of algebraic surfaces. So what is the connection between braids and art? So I'm going back to the Institute in Princeton 20 years after I was a postdoc there. I came there again, and every afternoon they had some kind of 20 minutes, every week they had 20 minutes on something that will address the whole community. They have mathematicians, physicists, historians, sociology, and also all the administration and spouses, etc., all the community. So usually mathematicians don't talk in that kind of something for the entire community. But they came to me, they said, maybe you can do it, so mathematics is represented here. And I gave 20 minutes on mathematics and beauty. Usually people think beauty in the eyes of the beholder. So I did two, and in the last one, I came into braids, because as I told you, braids, I'm so familiar with braids. So I came into braids, and there was a little old man there in the audience that was raising his hand when I did mathematics and braids. And even though these 20 minutes are very short and you're not supposed to, so I said, okay, he said, no, I'll wait for the end. So I continue with the braids, and then he raised his hand and he said, you learned it from Leonardo, right? So I don't know what he's told, Leonardo DiCaprio, I mean, was very famous there. I didn't know what does he want from me. Anyhow, this is Irvine Levine, one of the greatest art historians. And he was specializing in medieval art, and as you can see here, Renaissance, Baroque, modern painting. And he was extremely interested in the braids. He really could not. And then later we started to talk, and at the end, he asked me to write a small article to the newsletter of School of Historical Studies about braids. And I kept in touch with him for a few years, but I learned a lot about Leonardo and braids. It turns out Leonardo was extremely interested in braids. It was fascinating, maybe like the woman last night or myself. So we came to Leonardo. When you talk about admiring someone or about a role model, we will talk about role models in the course of this time. You have to look on someone to know, I can do it. If she did it, I can do it. If she did it, I can do it better. But we also have role models who are male. And Leonardo is such an interdisciplinary person. And nowadays, that interdisciplinary is back to be fashionable. They say that in the 20th century, everybody studied more and more about less and less. It was a little bit, you were expert on something very small. Now you understand that in order to do something to help humanity, in order to be able to improve human life, you have to be interdisciplinary. So we connect biology and mathematics and computer science and physics to do a lot of things. So it's not multidisciplinary, a lot of people, he was interdisciplinary into himself. So it turns out that he really studied the woman's braided hair. So he started in 1480. That's when he started. And this is the first drawing that I found. And as you can see, there are braids. Maybe there's some water somewhere. Is there? No. They are braided. The hair are braided, but they're also, the braids is turned like a spiral. So you have a braid that is turned like a spiral. And that's how he started with the braids and spiral. And if you go to a later drawing, 504, 5 to 506, you don't see the spiral anymore, but you see like discs or like circles that are the circles that are the braids. So this involves, so the braids with him are involving other geometrical objects. So spiral is a very mathematical object that we'll talk about it in the second semester. And, but circles, we don't have to, you know circles, so we don't have to talk more about circles. I'll make one break and say something about mathematics, because we say circles. Circles is the most symmetric object, the more close object, and many times you can see it. And everything started with the Greek geometry, so it's let's say 3,000 years. But whatever was true 3,000 years, thank you so much, whatever was true 3,000 years ago is still correct today. And that's the difference between mathematics and other fields. What was true in biology 100 years ago is not necessarily true today, but with mathematics, it's coming on. And all the objects, geometric all objects, are still very much visible and important. Okay, so here he did circles. She's famous. He called her Leda and Oleda, and she's very famous, and he did a lot of drawings of her. And here I don't have the year of that one, but it looks something in between the spiral and the circles. But anyhow, there are braids there, always. Either spiral or circles, it's made out of braids. And that's another very famous drawing by Leonardo of the same Leda. Somehow here, she teared her braids. They are only one small braid, but so you see the changes, the dynamic. And this is a wall art in the museum in London, and that's a wall art that shows different development. We saw these, I think the last one, the one below we didn't see, but we saw the other two ones, but this is put together there as to show development. And this is the back of the head of Leda, and here we have something else, not only the spirals, but like a net, like a grid, the grid of braids. Grid is something, and like line arrangement is something that you will learn tomorrow from Moshe Cohen. This was put for sale somewhere. It's a jewelry that inside you have like the head of Leda with some braids. I wouldn't mind having that as a gift, but you might go to Google, you might have some startup, you'll have this as a gift sometime. And then it was all put in a book, Leonardo by Leonardo, The Untold Feminist Power by Leonardo. So this is a book. You will get a very nice book later today, but this, I don't know if we can find 20 of these books, but you'll get it next semester. But the sentence I want to put in is The Untold Feminist Power by Leonardo. So we talk about braids, we talk about art, and this is something that we can talk to male and female. It's relevant to everybody. But he was a feminist in 600, 550 years ago, before feminism was even a word, before it was invented, before women had a chance to go and study at the university. There were very few universities, but in Italy there were already universities, but women were not allowed to study there. And he was telling this story. So I found it even more exciting than the moment that Levine told me, you learned it from Leonardo. So that was quite an exciting moment. But then to see that on top of everything, he was a feminist was also extremely exciting for me to hear it. There are many male feminists today also. It's not something unusual, but I'm talking 500 years ago. And I found out what you said about your daughter, the dean, that male that have daughters are more receptive to female in the workplace. And not only them, but I'm so grateful for the passion shared with Dr. Cantrell and the department about this project, but it's not always the case, but we'll talk about it. But Leonardo wasn't the only artist that that was fascinated by braids. When I started to look, I found also other artists. This I don't know the name, and this one I found. So you see that this is a different artist. I'm not an artist. I want to talk to the people in the art department here in UM. I just arrived 2 months ago, so I didn't have time to do everything, but maybe they know who is this artist. But this is already like when Lida took off the braids. Okay, mathematical braids. How is a braid even a mathematical object? This is a geometric object. Now, this is some kind of a three-dimensional object. Or if you look only on the cover of the braid, it's two-dimensional. But this is a geometric object in the universe. If it's a geometric object in our universe, it's a mathematical object, because geometry is always mathematical. But usual hair braids are 3 strands. As I said, that's what we learn to do in the kindergarten. But in mathematics, there are also 2 strands braid, 4 strands braid. We saw it also there in the original photos that I brought. 5 strand braids, but actually it can be n strand braids. N can be any number. Any number can you say 10. We can do a braid of 10 strands. We can do few braids of 10 strands. They will not be the same. And you cannot move from one to another. 2 separate types of n strands braid. So this is the 3-strand band, and this is connected to a braid group. I'm using a word that maybe is not familiar to you, group. I don't know how many of you learned it already, because we want to talk to freshmen and up. But you will hear a definition of this in the next lectures. But all braids of 3 strands create together or relates to a group, which is called the braid group on 3 strands. The 4 strands braid that we saw before related to the braid group on 4 strands. We call it braid group on 4 strands, or we say B4. To be short, we say B3. Or here, to be short, we say B4. So these are my friends, B3, B4, I hang out with them. And then there is the mixed strand braids. The mixed strands braids can be related to a way that the B2 is embedded into B3, embedded into B4, embedded into, and then Bn. N can be any number. So this is just first reflection how braids how braids are related to mathematics. But what do mathematicians study when they study the property of braids? They ask, how do braids relate to each other? If I told you a 10 braids, you can do something. You can take 5 of them and make a strand. You can take 5 of them and make a strand. Or you can take 2, 3, 3, 2, for example. You can do different. So you want to know what are the relations between that option and that option. Are they easily smoothed from one to another? So that's one of the questions mathematicians the do braid theory ask themselves. How they can be deformed from one type of braid to another type of braid. And can we order them? Numbers we ordered. We know that 10 is bigger than 7 and 21 is bigger than 15. But if we are going in the plane, it's not clear how is their order in the plane. Because if you take, let's say, 7, 2 in one point and 4, 5. So it's not clear who this 7, 2 could be here and 4, 5 here. So it's not clear if there is order. So not all group, not every sets have order in it. So can braids be ordered? It's a question that people were asking themselves. And how can a braid be factorized? Like if we have a number 21, we know 21 is 7 times 3. 35 is 5 times 7. And 12 is 2, 2, 3. So we factorize 12 to 2 times 2 times 3. But can we factorize braids? So this is another question that people are asking. And if you take the group of all braids, let's say B3, B4, B5, what is the structure of this group? Is B3 similar to B4, similar to B5, or what? These are the questions. Of course, answers is different, but that to give you the feeling, how does braids relate to mathematics? And the theory of braids and the dynamics has applications, so that's something important. It's always in mathematics. Even if you don't see that something is applicable, at one day it will be applicable. So a theorem that Fermat did 300 years ago is being used in the crypto system of your hotel room, that when you open it with a plastic card, you open your hotel room, there is a 300 years old theorem in that system. It's called RSA, the system. So there is this old theorem in there. But so braids is also applicable to cryptography, and that's something that I do now, to neural computation and to geometry of surface. I did it so that's important, but you'll hear in the course of 2 days other applications. It's deformed to another braid by conjugation. And without explaining it, I just say, what does this mean for hair braid? So I was just joking that one needs to wash his hair in order to make a new braid. So you cannot move from one braid to another. You have to undo it, wash your hair, and do a new braid. That's actually what Iran did. The connections of braids to geometry and to study of surfaces goes through the dynamic nature of braids, what we call monodromy of braids. Doesn't matter the word donomy, there's some dynamic in that. And this is the topic which is the heart of my research in algebraic surface, the dynamic. But it turns out that Leonardo wasn't only interested in braids, he was very fascinated by the dynamic of braids. So we go back to Leonardo. And being fascinated by the dynamic of characteristics of braids, he made a long series of drawings. I don't have all of them, how braids transformed into water. So this is Lida, that she has only one braid already there, and that's the end. This is the end drawing. So there is a very long drawings that start from this and end up on the other one. I added here flow of braids. In the center, I added here some flow of braids that were part of this long series. And that's flows of ideas. He wrote to himself some certain remarks. When he did it, he wrote to himself certain remarks about this flow. And I don't think that braid monodromy, I don't know braid monodromy influenced by him, but the fact that something is dynamic, that's how 500 years at the end. And then he also put braids into Watery Chaos, which he has these small remarks underneath in Italian that I did not translate, but I look at the drawings and I get it. Some of it were translated. And this is building river sea system. So he is taking the different braids. You can see clearly the braid here, and he's building from it structures in the sea and flow. And turbulence, one of the oldest unsolved problems in physics, I think the mathematics that has to do with turbulence is one of the clay programs, no? And Jim Carlson, that was the director of Clay Foundation, is nodding in the head. So this is the oldest unsolved problems in physics that he actually put it 500 years ago. We are very proud that Hilbert put in the beginning of the 20th century the 100 problems that needs to be solved in the 20th century. Not all of the problems were solved, but Leonardo put something 500 years before. And these reflections also, if you read a little bit, he explains how he moved from the different sides of LIDA, making sure that they are all correct. If you look, if you want to do a three-dimensional photo in a movie, sometimes, or if you want to build from two-dimensional photos, you want to build a three-dimensional object. You have to see that these two-dimensional objects are relevant. And then his last one was also with braid is the time traveler. I don't know about time traveler in life, but in movies and there are many time travelers. In the books, you can see many time travelers. Okay, the sentence of the day. I told you one sentence every time. So the sentence of the day has nothing to do with Leonardo and in braids. It's sentence about mathematics. So mathematics is the majestic structure conceived by man to grant him comprehension of the universe. Corbusier was one of the greatest architects of the 20th century, and that was his looking at mathematics. You see many times people saying different statements about mathematics. We will see in these days or in the future, we'll see many. It's how the public is looking on mathematics. I changed it a little bit. He didn't really say it, but instead of conceived by man, I write conceived by woman to grant her comprehension of the universe. So Leonardo was a feminist. Corbusier wasn't yet, but we'll have it. Architecture is very related to female and male, because you're building houses. It has to be good for both of them. Okay, so we made it to the appendix. I'm very happy about it, because how can you talk about Leonardo and not mentioning the golden section? So I'll do it very briefly, because that's not the aim of our talk today. But it starts with the shape of a perfect room that has a fixed ratio. B over C is 1.618. I think this room is not a square, it's a trapeze, but I think that if you do a little bit of approximation, this has a good proportion, this room, and you feel nice at it. That's part of the thing. Dr. Cantrell took the best room in the university. It's also good because of COVID, we have to spread you. So this, you are in a nice, perfect room. Another thing you say, that a perfect room, let's say it's a square, so B and C are the two edges. B over C is the big over the small is like the sum of the two over the big. So this is the shape of a perfect room. Oui. So these two properties of a perfect room are actually the same. It's not that that's one definition and that's another approach. It's actually the same. How is it the same? If you take B, let's start with one and make it to the other one. If B over C is B plus C over B, then it means that if I open the brackets and I called B over CX, then from B over C time equal B plus C over B, I get an equation x equals 1 plus 1 over x. And I multiply everything by x, and I get a quadratic equation. X squared equals x plus 1. If I solve it, you know how to solve a quadratic equation. I solve the quadratic equation, and I get that x equals 1 plus square root of 5 over 2. Now, square root of 5 is not a rational number, so I cannot write exactly what it is. But if we approximate it, then we get that x is approximately 1.618, but it goes more. So of course, when you do a perfect room, you don't do 1.618 and build one wall and multiply it by another wall, but that's how it is in order to feel at ease in your home. So B over C is 1.618. And they call this number the golden section because they found how fundamental it is in our life. So they called it the golden section and also the divine number because it's so fundamental. You can see it also in segments. It doesn't have to be a room. So B is the big one, C is the small one, A is both of them. So B over C is A over B. And you see many modern architecture buildings that are built with that. So this is the National Tower in Toronto, the one on the right. The one on the left is the United Nations. And you see the golden section in the proportion between the different sections in this building. And this is Corvaisier building. It has many golden sections in it. But it also was in antiquity. The Pantheon has many golden sections in it. The Taj Mahal has many golden sections. Different proportion is there. And the Notre Dame in Paris, this is an old picture. It unfortunately doesn't look like that today after the fire. But whatever, when you see the green and the white, so the columns are standing in reflection to each other according to the golden section. And this is a classical painting. Where do you put the main figure? So you don't necessarily put it in the center. You put it the place the proportion should be. Photographer, my daughter is a photographer, so she tells me they're always told where to put the main crocodile. I don't know where to put the animal. It should be always according to, they do some, and of course the ultimate diva. She has as many proportion in her face. There's many golden sections in her face as you can imagine. So it's not about beauty of that side, It's the different, and the more proportion it is, the more we feel that it's beautiful, regardless of generations. But Leonardo was the only one that really looked at the human body, the golden section in the human body. And his study shows that a perfect body in his eyes has this proportion between the upper part, above the navel, and the lower part. Maybe one day I'll show you a movie from a conference for International Congress of Mathematical Instruction that I took in Seoul. And in that, they put there some kind of a device that you move, you stand on the device and you move it and you put the center in your navel, and then you can see the proportion if it's okay or not. And there were a long list of women standing in line in order to check it. And it turns out universal, people from all over the world. So we came back to Leonardo. This is a very famous drawing of Leonardo, and he explained a lot of these things here. So Appendix 2, I guess I have the time, goes from visual experience to machine vision. When we talk about the golden section in different places and how do we feel about it. This is really something very small that mathematics is doing for machine vision. In order to imitate the vision that we see, it's one of the most difficult challenges in computational neuroscience, because even face recognition is very difficult. Sometimes a machine can do better than you, but most of the time you do better, because it's a cultural thing. Face recognition in the brain is a different location than geometry, forms where you identify forms in the brain. So where you identify a triangle is a different place than face, because it's culture dependent. My nephew has a small startup company that he is fixing what the machines are not doing well. So he has a software in Tel Aviv. A guy comes to a factory in North Dakota, and the machine looks at its face, and the door should be open. And suddenly the door is not opening. So when that does happen, they are sending his photo to Tel Aviv. They are sending the photo that they have in their database of this person to Tel Aviv. Maybe today he was sad, maybe he cut his hair. It doesn't matter what happened. Someone, not necessarily in Tel Aviv, maybe in India or in Japan, is looking at the picture and deciding. They have to decide very quickly if it's the same person, because the guy is standing in the cold outside. So then people are doing it, not machine. Then he does machine learning in order so that the machine in North Dakota will do it better. So his machine learning mechanism is killing his business, because slowly and slowly he's teaching the machine how to do it better. You will learn about machine learning tomorrow. Anyhow, so machine vision is a big challenge, not only in face recognition, but in other fields, and you're using a lot of mathematics in order to do it. But okay, I said what is machine vision? Is a machine sees something and recognize what it is. And why we need it? Because everything goes to AI, because there are electrical cars with no drivers, and because there are satellites in the sky that want to identify if this is a building or this is a nuclear site or whatever. And you have to teach the machine more and more how to recognize it. So I already said about face recognition that it's important, but not always easy, and also the question about beauty. So we want to replace human vision and identify objects. I just said it. It's important to help blind people that they see something, it's identified, and it tells them what they are seeing. It's important for medical diagnostic, for distance medicine, for automatic safety control in assembly line, and it's the last frontier in robotics. Robotics can be more and more useful, but vision sometimes stops it. And we want to understand the essence of visual experience, advanced three-dimensional cameras, and more. So the greatest challenge is face recognition. I already talked about it, so I'll pass it. And when I say that mathematics is in machine vision, and if we want to communicate precise and visual information, a machine will need to use mathematical notions, such as proportion, symmetry, axis, reflection, rotation, center, half-twist, periodicity, order, perspective, coordinate, cycle, space, intersection, continuity, noise, density, stability, smoothness, curvature, projection, threefold, convexity, and more. So all the words that we need in order to understand what we see are coming from mathematics. So mathematics will be is strong, and as it's developed, it's much stronger. So this appendix is to give you a little bit motivation. And finally, we say, can mathematics explain the origin and true nature of beauty, or can all expression of beauty be formulated with mathematical notation? Is beauty an absolute term? This is not for discussing now. These are questions that I put in the brain. This update on my research I don't see. And since this is the end, so I repeat again the sentence of the day. So mathematics is the majestic structure conceived by women to grant her comprehension of the universe. And in the last 1 minute that I have, I'll tell you the next attraction, what you will see, what we will talk about in the next semester that will be about geometry. So we'll talk about Fibonacci spirals in shells. Fibonacci is also a very strong mathematical object in cactus, in rose, in sunflower. We'll talk about mosaic, which also you think it's something, but it's very mathematic. I don't know if you know about the Dutch artist Escher. We'll also talk about this. And you cannot end a talk on mathematics and vision without looking at snowflakes. Well, you can't see so much of it in Miami, but we can see it whenever we want. Thank you very much for your attention.